All right, we left off having discussed the nature of the water molecule itself and how water is made up of two hydrogens and an oxygen. The oxygen is electronegative, and the electronegativity of the oxygen leads to water being polar. Water molecules are polar. They have little opposite ends that act like little magnets, and that is what gives water some really peculiar behaviors that many other molecules do not share. So, what we're going to talk about now are some of those properties or behaviors or characteristics of water that water has that are kind of unique to water that we don't see in other molecules and that are so very important for living things on Earth. Okay? So, all of water's unique properties are derived from its polarity. Its polarity, it's having little opposite ends. That's really important. Okay? So, the first property that we're going to talk about is that water is cohesive, meaning water likes to, and when I say like, please know, I don't think little water molecules have personalities and brains and all that, but they behave as though they like to stick to each other. So, for example, water likes to stick to itself, meaning if this is a water molecule, there's my oxygen, there's a hydrogen, there's a hydrogen. And this is a water molecule, oxygen here with two hydrogens. This slightly negative oxygen and the slightly positive hydrogen are going to be slightly attracted to each other, and we call that very weak bond a hydrogen bond. Okay? And if we had a bunch of water molecules, they'd all kind of want to stick together in that way. Now, examples of this in nature, we see, for example, this little guy here, surface tension that you all, I'm sure, have learned about before. The fact that water has kind of a surface that doesn't want to break. Little bugs called water striders can take advantage of that. They're so light and their little feet are designed in such a way that they can walk on the surface of the water without breaking these hydrogen bonds that kind of glue the water molecules together. Now, that's kind of a trivial example of the significance of this property. A much more important example of the significance of this property would be to talk about how if you are a tree, here I am, I'm a tree, here is the ground, and here are my branches that would have leaves on them. I need to get water from my roots that are down here in the ground. I need to get water up the roots, up the tree, into the leaves, okay? In order to do that, okay, water actually leaves the leaf surface through a process called transpiration, and you don't really need to remember that right now, but that's the process through basically water evaporates from leaves, okay? But because water molecules cling to each other, when a water molecule leaves from a leaf, it pulls the other water molecules up behind it from that are kind of holding hands with each other, so to speak. And so the water is pulled ultimately all the way from the soil up through the tree, up through the stems, the branches, and out through the leaves. And so we keep a constant flow of water moving through plants because water is cohesive, okay? It sticks to each other. The little water molecules hold hands and they pull each other up a plant like a choo-choo train. This is really important because otherwise water is having to defy the force of gravity. Gravity's pulling water down a plant. But in this way, because of water's cohesive nature, it actually, when it evaporates, it just gets pulled right up the plant. So that's really, really important. Additionally, water is adhesive. Now, if cohesive means water molecules stick to each other, water being adhesive means water will stick to other things as long as the other things are also polar or have a charge. Imagine trying to stick a magnet onto a piece of wood. The wood's not magnetic, so the magnet has no attraction to it. Well, it's the same thing with water molecules. They want to stick to other things that are charged or at least slightly charged. If the substance you're trying to stick the water to isn't charged or isn't polar, there's no attraction there. So as long as you are trying to attach water to something that is also charged, it will stick to it. Now, examples of why this is relevant in nature is something called capillary action. And again, the most important true function of this in nature is, again, getting water up a plant from its roots, defying gravity. Within a stem, there are many extraordinarily tiny tubes, okay? And because those little tubes inside plant tissue, called xylem and phloem and all that, but we'll focus on that later, these little tiny tubes are so tiny, and they are also polar, that when water gets up in them, it clings to them rather than falling back down. So the little tiny tubes are very polar. The little amounts of water that go up into each tube are not very heavy, so the capillary action, the adhesiveness of the water molecules for the sides of the tube is a greater attraction than the pull of gravity down. So again, we can keep the water going up the plants. And that, again, is really important for life on Earth as we know it. All these plants around us that we see are depending on that property of water. It also works in other things as well. All right, this is really significant, really super significant. Water has a high specific heat. So this is property 3. And basically what that means is that it takes a lot of energy to raise the temperature of water. Water inherently has a very stable temperature. Okay, and if you want to raise the temperature of water by 1 degree Celsius, you're going to have to pump a lot of energy into it. Now, conversely, once you have heated water, it can store a whole lot of heat. And that temperature remains pretty stable for a long time. Now, why is that true about water? First of all, again, it has to do with the hydrogen bonds, okay? If we've got 2 water molecules and we want to increase their temperature, so here they are, our 2 water molecules. Remember, this one is oxygen, this one is oxygen over here, and they're each connected to 2 hydrogens. So this is water and this is water. Remember, this slightly negative N and this slightly positive N will be attracted, and we'll get that little hydrogen bond right there. Now, if I want to heat up some molecules, I apply energy to them and the molecules start moving. That's what we sense as heat, is the collisions of those little atoms or molecules with our hand. We feel that as heat. Well, in order to make these guys start moving as we apply energy to them, the first thing we have to do is we got to apply a lot of energy just to break that hydrogen bond, so that then the molecules can really start moving around, and we see that, or we sense that as a heat increase, okay? So, because of these hydrogen bonds, then, you have to dump in a lot of heat to change the temperature of water. So its temperature is very, very stable, okay? Now, why is this relevant for living things? Because organisms that are largely made up of water, like you and me and every other living thing, it causes our temperature to be more stable than it would be if there was some other liquid that were the centerpiece of our body. Our body temperature is easier to maintain at a stable state because water is so stable, okay? And additionally, the temperature of the earth as a whole tends to be reasonably stable. And I know you might say, but it gets really cold and it gets really hot. Yeah, but not to the extremes that it does on some other planets where there's not as much water. So the temperature of the earth tends to be more stable, largely because of the way that water can store heat, lots of heat, and release it slowly, and it tends to have a very stabilizing effect on the temperature, okay? Also, water has what is called a high heat of vaporization. This is almost like what we just talked about. But instead of talking about just raising the temperature of water, we're saying that it takes a lot of heat energy to make water vaporize, which means to make water go from a liquid to a gas. In other words, go from liquid to a vapor, which is another word for gas. Now, why am I showing you a picture of some sweaty dude doing push-ups? Okay, because one of the things that this property of water, having a high heat of vaporization, does for us is it allows us to rely on evaporative cooling to cool our bodies. This guy is sweating. His body is trying to cool himself, cool him off as he's exerting himself. Well, how is that happening? Because when you sweat, this liquid is on your body. It doesn't cool you, though, until it actually leaves your body, until it evaporates away. Because water is hard to vaporize, in other words, it takes a lot of energy to vaporize it, when you finally have given enough heat energy from your body to vaporize a water molecule into the air, that water molecule takes a whole lot of heat energy with it when it goes. So the water molecule leaving this guy's body, because his body got so hot, it made this water molecule vaporize, it took heat with it. Now, when it takes heat with it, this guy feels cooler, and that's how evaporative cooling, which is right here, evaporative cooling, that's how that works. Same when a dog is panting or anything like that. And same when an animal, like any turtle or whatever, gets wet and the water evaporates off of them, they would feel cooler because of it. They can't sweat. They aren't like us, but there are other ways. Now, additionally, the high heat of vaporization is important because obviously we have lots of water around. It hasn't all vaporized into outer space. That's because water has a high heat of vaporization. It's hard to make it vaporize. So we still have lots and lots of liquid water on our planet because of it's stubborn to get to go into vapor. And so we don't lose all of our water into the atmosphere. So that's a good thing. All right, another peculiar property of water is that ice floats. Now, think about this. I think this might be number 5 or 6. I can't remember. Ice floats. When a substance gets cold, the molecules in that substance slow down. They aren't moving as much. Remember, it is heat energy that causes things, or energy that causes things to move, and when they move, they tend to get further apart. When you take energy away, the molecules slow down, and they tend to get closer together. And when things get closer together, they tend to get more dense, okay? So, in normal situations with normal substances, when we make them more dense, we bring the molecules closer together and make some very, very dense substance, okay? If that same substance is in liquid form, the liquid form will tend to have its particles spread more widely around, and if you drop the solid of the same material into a liquid form of the same material, the solid form will tend to sink because it's more dense. Water is exactly the opposite. Anybody that's ever dropped an ice cube in a glass of water or has skated on a pond that is frozen like this one knows that the ice is going to be on top, not down at the bottom. Again, this is because of the hydrogen bonds between water molecules. Water molecules do slow down when you get them cold, and they do get close together to a certain point. But then those little hydrogen bonds kind of kick into place and prevent those molecules from getting any closer together when you're making ice. And so truly the ice ends up being less dense than some chilled liquid water, okay? So what this means for living things is very important. Ponds don't freeze solid. The ice does not freeze and sink down to the bottom, because if it did, you'd end up with just a stack of a solid block of ice in your pond. What does happen is that the ice freezes on the top and creates a kind of insulating layer. So here's my pond, here's my ice that's frozen on the top, but underneath it, Mr. Fishy can still swim. Okay, because the water is insulated from the super cold air that is really where the cold temperature is originating from. And that cold, super cold air can't penetrate too much further than the ice that's frozen on the top. And so this water remains liquid underneath. And so the aquatic organisms can survive over winter under normal conditions that way. And that applies to oceans as well. Okay, so really important for life on Earth, surviving in the cold. Okay, now, I think this is number 6. Water is a great solvent. Sometimes we call it the universal solvent. That's a little deceptive. Yeah, here you go. Because it doesn't dissolve everything. But as long as the substance you want dissolved, the solute you want dissolved is polar, meaning water would be attracted to it, then it will dissolve it very well. Think salt. Salt is highly polar. It's charged. It's made up of a positive sodium and a negative chlorine. And what happens is the little positive ends of water molecules that we see here, the hydrogen ends, will be attracted to the chlorine. The negative ends, the oxygen ends of water molecules, if you drop the salt into some water, will be attracted to the sodium. And the next thing you know, the powerful attraction that these water molecules have for each of these ions will just bust them up. And if you look down here, the chlorine is surrounded by the little positives of the hydrogens, negative attracted to positive. The sodium, which is a big old positive, is attracted the little negative ends of the water, the oxygens are attracted to it, and they just kind of get in there and separate these two ions from each other, and it dissolves it. And many polar substances act that way in water. Non-polar substances will not act that way. Okay? And that brings us to our last important property of water, is that water tends to organize non-polar substances. Meaning, if you've got some stuff that's not polar, it's like having wood next to a magnet. They're not interested in each other. Okay? If you've got wood and a magnet, and you throw them all together, the magnets want to play with each other. They're not interested in the wood, and the wood's not interested in this, just wood. Okay? Same goes for water with non-polar substances, like lipids. Another way of thinking of lipids is fats and oils. And if you've ever had oil and vinegar salad dressing, you know you have to shake it up before you pour it on your salad, because the oil, which is a fat, a lipid, and the vinegar, which is a water-based substance, they don't mix very well. And the reason is because the vinegar and the water in the vinegar is really attracted to each other, but the oil is not polar. It's non-polar. And it's just like magnets with wood. They're not interested in the wood. The water's not interested in the oil. And so it separates the oil. Why is that important? Because as we'll see later on, cell membranes are made of kind of fatty substances called phospholipids, and you don't need to remember that. But because of the way water acts when in the presence of phospholipids, we can create cells. Our cells are created by that interaction. Water will kind of push the phospholipids, the non-polar molecules, into little packets that make cells. And if that weren't the case, I don't know that cells would ever have been created on Earth, because they depend on this interaction of these non-polar fatty molecules with polar water kind of pushing them to make these layers that we recognize as cell membranes. So we'll talk more about that later when we get to cells, and it might make more sense then than it does right now. Okay, With our next job is to talk about pH, but I think I will save that little funness for class. So we'll talk about pH later. Just remember your 7 properties of water: cohesion, adhesion, high specific heat, high heat of vaporization, ice floats, universal solvent, and it organizes nonpolar molecules. Okay, that's it for now, and I'll catch you next time. Thanks for watching.